Welcome back to Neural Intel. Today, we're diving deep into a really fascinating technical challenge. How do you make these massive AI models selectively forget specific information, but without, losing everything else they've learned?
Yeah, you shared a really intriguing paper with us from Archive called Practical Continual Forgetting for Pre-trained Vision Models. And it really gets into a problem that's becoming more and more important.
Absolutely. I mean,
Yeah.
think about it. These huge AI models are trained on just vast data sets, right?
Yeah.
And inevitably, some of that data might become outdated, maybe it's just wrong,
Hmm.
or for privacy reasons, it needs to be removed. So this ability to precisely erase specific bits of knowledge is becoming critical.
Exactly. And the paper specifically highlights this scenario where erasure requests might come in sequentially, like over time. Users or the model owners might say, forget this, then later forget that. They call this continual forgetting.
Right, continual forgetting. And the challenge is, how do you handle this ongoing stream of requests without wrecking the model's overall performance?
That's the core technical problem. And the paper points out like three main hurdles.
Okay, what are they?
Well, first, just efficiently and effectively deleting the unwanted knowledge. That sounds simple, but technically it's not trivial.
Hmm.
Second, minimizing the damage to the rest of the knowledge. You don't want to cause what researchers call catastrophic forgetting, where deleting one thing makes the model forget lots of unrelated things.
Okay, that makes sense. Avoid collateral damage. And the third?
The third is handling situations where the data you have, either for the stuff you want to forget or even for the stuff you want to keep, might be scarce or incomplete. Very practical concerns, you know?
Yeah, definitely.
Yeah.
You might not always have perfect data to work with. So how do you perform this kind of AI brain surgery precisely without causing amnesia, especially when your surgical tools or guides are maybe limited?
That's the crux of it.
So our mission today is to unpack the technical innovations these researchers propose. We'll dig into their methods, the mechanics behind them, and look at the experimental results they present. Okay, let's start with their main approaches. GS-LoRA and GS-LoRA plus LoRA.
Right. So they introduce Group Sparse LoRa, or GS-LoRa, as their sort of baseline technical method. But then, realizing that real-world forgetting often happens with limited data, they enhance it to create GS-LoRa plus WAR.
Okay, let's break down the tech. Big piece of this puzzle is LoRA. That's low-rank adaptation. Now, just briefly, LoRA is a way to fine-tune these huge pre-trained models more efficiently, instead of messing with all the billions of parameters.
Yeah, you just add these small, low-rank matrices to specific layers, usually the feed-forward network, the FFN modules inside the transformer blocks.
And the key technical point here for forgetting is that only these small LoRA matrices get trained or adapted, right? The original massive weights of the model stay frozen.
Exactly. That makes the whole forgetting process much more computationally efficient. Fewer parameters to fiddle with.
Right. It's like making tiny adjustments to a couple of key components
Yeah.
instead of rebuilding the whole engine. Okay, so that's efficiency. But what about the second challenge, not forgetting the stuff we want to keep? They use something called a group sparse regularizer.
Yeah, this is where it gets technically quite clever. They treat all the LoRa modules within an entire transformer block as a single group.
A group, okay.
And this group sparse regularizer, well, it encourages the algorithm to be selective. It basically pushes it to modify LoRa modules only within the most relevant transformer blocks for forgetting a specific task, while leaving the other blocks mostly untouched.
Ah, so it's like identifying which parts of the model's brain are most involved with the knowledge to be forgotten and focusing the changes there, like targeted surgery.
Precisely. It encourages sparsity at the group level, meaning most groups, transformer blocks, should ideally have their LoRa modifications zeroed out.
And technically, how's that achieved? You mentioned the loss term?
Yes, they add a penalty term, the L structure loss, to their objective function. This term penalizes the Frobenius norms of the LoRa matrices within each group. Basically, it pushes the norms of the LoRa matrices in most groups towards zero. A zero norm means no effective change from the LoRa module in that block.
Got it. So maximize sparsity across the blocks, concentrating changes where they're needed most. Okay, that's GS-LoRA. And GS-LoRA plus AC. What's the AC plus added? You mentioned prototype regularization.
Exactly. The LoRa add is all about adding this prototype regularization, and it's specifically designed for those tricky practical cases, especially the few-shot scenario where you have very little data representing the classes you need to forget.
Right, the limited data problem.
Yeah.
So how does this prototype regularization help technically? What is a prototype here?
So think of a prototype as a representative embedding, like a central point or vector in the model's internal feature space that captures the essence of a class. The researchers calculate these prototypes before forgetting, using the model's outputs just before the final classification layer, the pre-softmax logits.
Okay, so they grab a snapshot of what the model thinks each class looks like internally before they start the forgetting process.
Precisely. Now, during forgetting, for the classes being forgotten, GS-LoRA array++ uses a specific loss function, they call it lprof, based on callback Libler divergence to actively push the model's current predictions away from those original prototypes.
Ah, so it's not just ignoring the class, it's actively teaching the model. Whatever you're outputting now, make it less like this prototype of the forgotten thing.
Exactly. It uses that prototype as a negative target, essentially. And conversely, for the classes being retained, it uses another KL divergence loss, lbror, to pull the predictions closer to their original prototypes.
Okay, so it reinforces the representations of the classes you want to keep, using their original prototypes as positive targets.
Right. This provides extra guidance, especially crucial when you don't have much, or maybe even any, new training data for the retained classes during the forgetting step. It helps stabilize their representations.
Very clever. It uses the model's own past understanding as a guide for both forgetting and retaining, particularly useful when external data is scarce. Okay, so technically sounds promising. How did it actually hold up in experiments? They tested it quite a bit, yeah.
Oh, yes, extensively. Across different vision tasks, face recognition, image classification on ImageNet 100 using a vision transformer, BITB16, and even object detection using deformable DETR on the COSO dataset. Testing across these different setups is important to show the method isn't just a one-trick pony.
Good range. And they compared it against other methods.
They did. A whole suite of baselines from continual learning and machine unlearning fields methods like EWC, MAS, LWF, ADR, FDR, scrub, and critically, also against just retraining the model from scratch on the remaining data, which is often considered a sort of upper bound, albeit usually impractical.
Okay, and the results for GS-LoRA+++.
The results look pretty strong, actually. Consistently, GS-LoRA++ managed to significantly drop performance on the forgotten classes, effective forgetting while maintaining high accuracy on the remaining classes. Minimal catastrophic forgetting.
Impressive. You mentioned they even tested forgetting like 90% of classes in one task.
Yeah, and the face recognition experiments. Even when asked to forget a huge proportion of the learned faces, their method showed promising results compared to many baselines, maintaining better accuracy on the faces it was supposed to remember.
Wow, that speaks to the precision.
Mhm.
And you also mentioned this tunable ratio is much smaller. What's the technical significance there?
Right. The tunable ratio is the percentage of the model's parameters that actually get modified during forgetting. GS-LoRA++ achieved its results by tuning significantly fewer parameters in some cases, less than 1.3% of the total model parameters.
Less than 1.3%. Compared to retraining the whole thing, that's tiny.
Exactly. It's a huge win for efficiency. Imagine updating these giant models if you only need to tweak a tiny fraction. It saves immense computation time and energy, makes continuous updates much more feasible.
Absolutely crucial for practical deployment. Did they test the continual aspect directly, like forgetting set A, then later forgetting set B?
Yes, they did sequential forgetting experiments. And again, GS-LoRA++ performed well. It forgot the target classes in each sequential step without drastically impacting the classes retained from previous steps, or even messing up the forgetting of classes from earlier steps. They measured this old accuracy to show it wasn't unraveling past changes.
That's key for a truly continual system. It needs memory of past operations, both retention and forgetting. And what about those tough, practical scenarios? Few shot and missing class data.
That's where the I++ pop part, the prototype regularization, really shone. In the few-shot setting, having the prototypes helped prevent the model from just overfitting on the handful of examples it had for the forgetting task.
Good.
And in the missing class setting, where some retained classes had no data during the forgetting step, the prototypes helped pull their representations back towards where they should be, mitigating catastrophic forgetting for those classes specifically. It showed good data efficiency.
So that prototype regularization really adds robustness when data is messy or incomplete. Makes sense. They also did an ablation study on where to put the LoRa modules, attention or FFN.
Yeah, they checked if it mattered whether they applied LoRa to the multi-head attention parts or the feed-forward network parts of the transformer blocks. Interestingly, the results are pretty comparable.
Huh. So knowledge relevant for forgetting seems distributed across both components.
It suggests that yes, both attention and FFN modules seem to store information that can be targeted and modified by this LoRa-based forgetting approach. It gives some flexibility in implementation.
Interesting technical insight into model internals. Now, one really critical point they address is the model truly forgetting or just pretending, like masking the output.
Yes, this is a super important technical distinction. Is it real forgetting happening deep in the model, or just deceptive forgetting where the output layer is manipulated? They called their approach backbone forgetting and compared it to just zeroing out the output weights for forgotten classes, which they called head forgetting.
Okay, how do they test the difference?
They did a recovery experiment. After forgetting, they froze the main model, the backbone, and tried to retrain only the final output layer to see if it could easily relearn the forgotten classes.
Oh, okay. So if the knowledge was still lurking in the backbone, just retraining the head should bring it back easily.
Exactly, and that's what happened with the head forgetting baseline. It recovered the forgotten classes quickly. But with GS-LoRA plus on, which performed backbone forgetting, retraining just the head struggled significantly to recover the performance on forgotten classes.
So the information really seems to have been removed or fundamentally altered within the model's main representational layers, not just hidden at the output.
That's the strong implication, suggesting a more robust and genuine form of forgetting. It's not just surface-level suppression.
That's a crucial technical validation. Okay, let's wrap up and think about the implications. For our listeners, this research really presents a technically sophisticated and quite practical approach to this growing need for AI models to forget selectively.
Yeah, the combination of LoRa for efficiency, group sparsity for targeted modification, and then prototype regularization for robustness, especially under data constraints, it offers a compelling technical recipe.
And the efficiency point, achieving significant forgetting with less than, say, 1.5% parameter changes, is just huge for scalability as these models get even bigger.
Absolutely. And that distinction they draw between real backbone forgetting and deceptive head forgetting is technically vital. It shows they're aiming for a deeper, more fundamental removal of information.
So this deep dive gives you a solid handle on the technical mechanics of state-of-the-art work in machine unlearning and continual adaptation. It really highlights the technical challenges and potential solutions for making AI more adaptable and manageable over time. What stands out most to you technically?
For me, it's the elegance of that group sparse regularization. Using the transformer block structure itself to guide the sparsity and target the modifications feels like a really neat technical idea. And I'm curious how well this might generalize beyond vision to, say, large language models. That's another huge area where forgetting is needed.
Good point. Well, for listeners wanting to dig even deeper into the technical nuts and bolts, the paper is on ArcSpore and the code's on GitHub. We've put the links in the description.
Definitely worth checking out if you're interested in the implementation details.
Thank you for joining us on this technical exploration into AI forgetting. We'll be back soon with another stack of sources. And remember, for the latest on AI and ML research, check out our webpage, linked in the bio.